Hello, my name is Kai Wen, and in this video I'll be giving a quick overview of our paper, Conditional Language Policy, or CLP, a framework for steerable multi-objective fine-tuning. And this is joint work with an amazing list of collaborators shown on the screen. First, let's recall what's typically done in RL fine-tuning, a crucial stage for post-training language models. At a high level, the RL algorithm receives a prompt, generates a response conditioned on the prompt, and then receives a real valued reward. With this reward feedback, the algorithm updates the model to maximize the reward. Successful algorithms for this include PPO or reinforce. However, a key limitation is that this setup is fundamentally single objective, and we can only optimize one reward function. This is an issue because in practice, there's a plethora of use cases and user types which cannot be captured by a single reward function. For example, we probably want our models to be factual and grounded. But we also want models to produce high-quality responses that are helpful. And third, we want our models to not cause harm. These are three common objectives that are fundamentally in tension, because on the one hand, optimizing for factuality will lead to shorter responses because they're easier to ground. On the other hand, optimizing for helpfulness will lead to longer and more thorough responses, but likely they're going to be less grounded. And finally, optimizing for safety will of course render the responses less helpful in general. So, this leads to the natural question: how should we deal with multiple conflicting rewards? Well, the common practice that's been used to train state-of-the-art models is to linearly combine these separate rewards with fixed weightings, denoted here as W1, W2, W3. By combining the three rewards in this way, we have effectively projected them into a single scalar which can now be used for RL fine-tuning. But unfortunately, this has a couple of drawbacks. First and foremost, the final model is not steerable, as the weightings vector is fixed at training time, cannot be changed at inference time. Moreover, a single objective doesn't really reflect the plurality of users and use cases, right? What we ideally want is a model whose reward can be steered to serve all users and all purposes. Finally, the reward weightings, well, they're essentially hyperparameters, and tuning them can be quite expensive. To address these issues, we proposed an alternative framework using multi-objective reinforcement learning, where the fine-tuning algorithm can now accept multiple rewards as feedback. We formalized this using a vectorial reward function, where each element of the vector is a separate reward. The key idea then is to learn a conditional language policy, or CLP, that can condition on both the weightings and the prompt to generate a response. In particular, the model condition on W should be Pareto optimal for the corresponding weighted reward, which is W inner product with the reward vector. Thus, CLP is steerable, since it can condition on the reward function at inference time. Concretely, the user can effectively steer the model to output different points along the Pareto curve by inputting different weightings for the same prompt. The key takeaway from our paper is that CLP affords two performance improvements compared to existing state-of-the-art. First, CLP Pareto dominates the rewarded soups baseline, meaning that it pushes the Pareto curve out along all dimensions and improves the reward along all dimensions. Second, CLP is more steerable than the prompting baseline, meaning that it can cover a wider spectrum of behaviors at inference time. Now let's get into the technical details, where a natural question arises. How can we condition a model on the weightings? Do we just feed it in as part of the prompt? Well, this is indeed a natural baseline, and we call this the prompt conditioning baseline. This conditioning mechanism is easy to implement and doesn't require changing the architecture of the neural net, which is very convenient. However, we found that prompt conditioning is often not very steerable, especially for smaller models. Thus, we opted for a more robust conditioning mechanism that conditions via the parameters of the neural net itself. And this idea is inspired by rewarded soups. Concretely, we maintain one copy of parameters per reward and linearly combine these copies using the given reward weightings. And of course, this can be done for any subset of parameters. The main benefit here is that parameter conditioning is very steerable, more sample efficient, and more robust than the previous prompting conditioning mechanism. However, this approach does copy some extra parameters, so the extra overhead scales with a number of rewards, which can be an inconvenience. Fortunately, we found that it's enough to use a small subset of conditional parameters to achieve good steerability. For example, we just need to use the first few attention layers as conditional parameters, and the rest of the network can remain unconditional, which doesn't use any more parameters. Thus, the overhead is not that restrictive, and CLP can achieve steerability while maintaining parameter efficiency. Now that we know how to condition on the weightings, let's look at the training objective. There are two expectations. The outer expectation samples the weightings vector for both the reward and the KL. This can be viewed as sampling from a task distribution, where each weighted reward or KL is a separate task, and we're just doing multitask learning over the continuum of tasks indexed by these vectors. The inner expectation is the classic RLHF objective with a condition policy on the weighted reward, and therefore classic algorithms such as PPO or reinforce can be used to optimize this. In our experiments, we just used reinforce with a value baseline. A good default for the task distribution Q is the uniform Dirichlet distribution, which we use in our experiments. Another narrower choice is to just sample corners of the distributions, corners of the simplex, and doing so recovers rewarded soups. Finally, the setup is very general, so you can pretty much specify any region in the simplex that you care about, and we also provide some ablations on this. Next, I will show a brief vignette of experiments, since that's all I have time for. We consider 2 summarization datasets and 3 reward functions. The first reward is Rouge, which measures text similarity between the generations and the ground truth summary. The second is NLI, which is a reward model that measures entailment and factuality. And third, we have a model called TLDR, which measures the quality of the summary based on the TLDR dataset. And if you recall from before, NLI is pretty much just the factuality model that encourages shorter responses, and TLDR is a quality model that encourages longer responses. As for which models we use Flan T5 with sizes shown on the screen. First, let's consider a 2 reward setting where we pick 2 out of the 3 rewards and plot Pareto curves that illustrate both Pareto dominance and steerability. Recall that Pareto dominance is how far we push out the curve along the reward dimensions, and steerability is how much we can stretch out the curve without collapsing to a single point. We compared against 2 baselines, rewarded soups, denoted as RS, and prompt conditioning, denoted as prompt. For CLP, we use 3 versions. Full CLP, which conditions on the full model for parameter conditioning. Attention CLP, which only conditions on the first few attention layers, and therefore uses much less memory. And Logit CLP, which conditions only on the last unembedding layer, and is equivalent to logit mixing, which we prove has some nice theoretical properties. We see that CLP and prompting, they both Pareto dominate rewarded soups, or RS. We also see that full CLP and attention CLP are much more steerable than prompting. Notably, attention CLP actually achieves essentially the same steerability as full CLP, despite using much fewer parameters, right? Because it only conditions on attention weights. We also conduct an ablation study on whether combining parameter conditioning and prompt conditioning can further boost steerability. And we found that prompting does not reliably improve steerability, although it doesn't degrade it either. So most of the performance is already afforded by parameter conditioning. To summarize, multi-objective fine-tuning with CLP has many benefits. First and foremost, CLP enables steerable inference, where the user can specify their reward at inference time to steer the model behavior. This in particular captures the plurality of users and use cases with one single conditional model. Finally, there's no need to sweep the weightings hyperparameter anymore, because one single CLP run will optimize all possible weightings simultaneously. So thank you for making it this far. Please check out our paper in this QR code for many more experiments and ablations. And in this paper, we also provide theoretical results, including conversions of logit mixing and kind of justifying why zero-shot methods like rewarded soups can work at all. And moreover, when this condition fails, we show a counterexample where CLP succeeds, but zero-shot methods like rewarded soups provably fails. So thanks again for your attention, and I look forward to discussing with you at EMNLP.